Safe Software is pleased to present the 2009 FME International User Conference. This session is presented by Ulf Manson, a GIS consultant with SWECO. Ulf has more than 15 years of experience with GIS and has been using FME for more than 10 years of that time. He is also an FME certified professional and is known as the founder of the FME art movement.
Thank you. I was a bit worried here before if you might have a problem with my Swedish accent. Now I know that we can get Dale over here to interpret because he showed some excellent Swedish language skills in the presentation earlier today. I will like a brief introduction to SWECO here. I can say that we are an engineering consulting company, so as Sweden is quite a small company, we like to brag about how big this company is. That's one way to look at it. I work as a project manager often, and I've come to learn that being a project manager now means that everybody else in the project gets to do the fun, while I explain to the client, or the customer in this case, why are we over budget and why we are late. So I don't know if you recognize this, but that's kind of how it's turned out after using FME for 10 years. So it can be interesting to see how we operate. We are divided into different areas. So we have, as you see, we have a lot of engineering stuff going on, but quite a lot of focus in water and environment. And I'm kind of working in the stuff below here. It's just 2% of what we do, but we kind of support the rest of our organization. We're doing GIS, back-end support, and of course a lot of FME work, which you can understand if you see what we do in these areas. I'll just sort through this. This case study I will talk about here is also related to environment, but these are kind of sample projects we've been involved with. And this is about flooding too. It's also related to the case study we'll look at. Also done some work in China now. Now, if we look at this case study, the main purpose here was to investigate the climate change and inundation in the municipality of, as how now Dale would pronounce this, Kävlinge, Sweden. That's more, Kävlinge is more the correct pronunciation though. It has these two dots here though. I don't know, the term inundation is, the specialist at SWECO who told me that I should use this terminology because if you say flooding analysis, it's kind of more such, they think it's a more dramatic thing than inundation, but it's a kind of similar thing. What we used FME for in this project was to create the terrain model, so they were able to conduct their cross-section analysis and also this inundation analysis, which in theory can be quite a simple operation. You just create a workbench and you insert a 3D point creator and you use some of the digital elevation model creators. You can use a surface model or something like that. But if you have laser scan data in as your source, there's quite a lot of information in there. So it's a bit more complicated just going at it. Now, a quick look at where this work was done is in. So Dale got here. In Kävlinge, we're talking about here, in the southern parts of Sweden. And this is in Sweden is a quite interesting area because it has some interesting geological features, and it's also known to have one of Sweden's few nuclear power plants, and it's placed facing towards Denmark. It's very close to Denmark, if you see here, which kind of made them angry all these years, but they don't use any nuclear power plants. But it has now been shut down. But it's, yeah, congratulations. But that's, that's kind of the background here. This municipality, they clearly recognize the need to plan for climate change and the possible effects in this area. And if you are a municipality with nuclear power, this is clearly important if it's close in the coast area. This is how the project was organized. We had a couple of from the environment team. They are specialists in water resources and environmental analysis. And as I explained earlier, there we had a geographic team where I worked and a colleague of mine. So we kind of supply these with the data they need. The specialists here in this case, they use all kind of different GIS tools. They use ArcGIS. They use, in this case, MapInfo with vertical mapper extension. I don't know if everybody's familiar with that one. But they also use different tools like Mike 11, or there's a lot of hydrological tools that you might have heard of. So we supply them with the data they need. But they're kind of responsible for doing the actual analysis. Now, the municipality provided us with a laser scan data set in this. It was about 700 text files full of 3D points. And what I'm showing here is the very basic Workbench, how you can examine this data. It just throws in just a text file reader that creates the points and throws it to a universal viewer. Though. A LiDAR reader and some effective reader, and that would be greatly appreciated, because this takes a while to examine data in this way. But this is the most basic way of getting some understanding what you look at. But it's kind of hard to get a feeling for what is this data really actually looking at if you can't view it in the third dimension. Now, everyone that has taken a training class by SAFE know the importance of data inspection. It's one of the first things you should do. And as we didn't have the spatial data inspector at this time, we made this very simple little workbench to try to visualize these text files in 3D. So we created a 3D PDF file. And this is actually in the stage where you just kind of getting to know the input data. So there's just the text file in here, and then we have some expression evaluated to exaggerate the elevation of each point. And we create a 3D point, and we also make some kind of extrusion here to get this data more easy to look at. So if you extrude it, it's easier to kind of see the surface in the laser scan data instead of just plotting the 3D points by themselves, so you can turn them around. Now, the destination data demands by the specialist team was quite clear that they should use the vertical mapper extension in MapInfo in this case. So we had to get that one right. We had to write that format right. But there also the issue in Sweden of coordinate system, which is kind of a big issue in Sweden, because each municipality a lot of the municipalities have invented their own coordinate system. So when you get data in the national reference system, you have to merge these systems. And in this case, we also had to think about how to create a manageable file size. So you can't just throw a 10 gigabyte vertical mapper file into MapInfo, at least not on our computers. It certainly wouldn't cope. It wouldn't open. So there's a trade-off here about where you have to create enough resolution in the digital elevation model and a manageable file size. So to get this right, first of all, so to get the data right, even if I've been working with FME for a pretty long time, I often do a mistake. If someone asks me for a special delivery in some special format, I just often, by mistake, start by reading the sort data. I throw destination data in. In this case, I have never produced vertical mapper format before, but I just throw it in. And if I spend a lot of time with it, I consult the readers and writers documentation, try to get this right, and then deliver the data to the guys requesting it, and they open it in their system, but it won't work because it's probably some coordinate system that gets tagged wrong, even if I've been doing this for a while. So the correct way of doing this is, in my experience, to ask those guys, give me a sample file, or create a simple sample file where you have the coordinate system correct, where you have the number of bands in the raster file correct, or where you have the correct schema in a geodatabase. Then it's much easier for me to create this in FME because I can just look at this. I can look at it in the FME viewer. I can use Workbench to get the schemas and data out there. So that's the way to go. In this case, I remember them to serve me a sample file, and everything went smoothly. Now, we must remember here that we had quite a lot of input files. So to start getting this right, we created a sample test workbench where we should get one tile to work correctly with the correct resolution and coordinate system, as I said, so we could see that it operated correctly in the vertical mapper environment. And this was also, it's not many transformers just to do this for a single file. We have the text file in here, and we do the 3D point replacing, and we do the raster digital elevation models generator here, and we do some other stuff here to get it right. Now, this is easy to kind of throw together, but the tricky thing here is getting these settings right. And this is one important thing to think of. When you work in the workbench, it's kind of easy to throw these workbenches in, but what does it mean if I use some kind of interpolation algorithm in here? Should I use nearest neighbor? Should I use the average 4 or 16? In this case, we are lucky because we have specialists who know this algorithm. They can tell us what we need. And then I consider myself just a techie in this case. I do what they tell me to use because they can relate to that. But it's something that you should never forget. Even if it's easy to throw the transformers in there, you should really think about what the settings mean in the end. Now, this simple test file where we just created one tile concluded that this will take a while because we had to resample the data quite heavily. I think we ended up with a gigabyte sized vertical mapper file in this case, and doing some simple math there concluded that this would take about 48 hours to complete the entire data set. And that is okay. That could be fine because we could run this over the weekend and it would be okay. But as I said, what I mean with this is we could, of course, try to use the fan-in option where we just merge all these laser scanned files in one workbench, and we create the files and we just do a fan out on them. But that would probably not work. But quite sure there would be errors in some of these files, and there should be a more structured approach to get this working. Now, traditionally, we would probably approach this by creating some kind of command line file or using a scripting tool, or maybe writing a .NET program. Something we have done before in similar cases. Now, Peter, yesterday, you gave the presentation about just for fun, and you were talking about actually this, how you can drive something like this. And this gets increasingly and more important if we work with 3D data sets, because that would mean that we have much more data and more volumes to work through. So this, you have actually added two very important transformers. It's a reader actually, and this is the FineM path reader. I don't know how many have used this one. This one in combination with the Workspace runner is really a really great thing, because what it does, the file path and memory just reads where the files are. You can throw in a wildcard and you get a list of all the files and the path to the files. So in this case, when we run this, I would get a list of, I would get 700 features, which only is a path to the laser scan data in this case. And with the help of the workspace runner, I can send this path to the previous workbench that actually only worked on one tile at the time. So this means that I can drive the entire translation process like this. But there is also this thing here, succeeded and failed. So this means that you can actually see what files, as you see, this is a simple representation here, but we can visualize or send to a log file the tiles that wouldn't go through correctly. And in the case what's actually means succeeded or failed, you can use the terminator, for instance, in the workbench that you call. If you have some quality checks in there, if this is okay or not, you can signal if you have succeeded or failed. So it's not just if there's something wrong with the actual file, but it can be something with the schema or the data in this case. What we also figured out that you can use this workspace runner to kind of optimize the use of your single desktop computer. So if you have 2 cores, for instance, if you're a bit clever, you can use the option, I think it says don't wait for completion, and something like that. That means it would just run the workspace and continue with the next feature that comes in. So if you're a bit handy there and a bit creative, you can actually run some kind of parallel processing on the desktop with this. It's kind of the poor man's FME server solution. Of course, the best option if you actually have a lot of engines or an FME server instance, it's kind of approaching this with the desktop approach. Now, the result in this case were a data set where we had 700 different elevation models, or tiles in this case. And if what we found out there was that if you have all of these tiles in a uniform resolution and coordinate system, it's very fast to glue them together to the single vertical mapper tab file in this case. I can't remember, I think it was 15 or 20 minutes or something like this to glue all these 700 files to one file. So if you don't have to do some special transformations with the raster files, or in this case it's kind of quick to create tiles and also merging tiles. Now, this is how it looked in operation in the actual vertical mapper application. That is a tool that is run in MapInfo. So you can see here that this is the Kävlinge River that goes through here. And there's probably been a cross-section drawn somewhere here, I would guess, so you can see the elevation in perspective here. What I really would love to be able to do is to use the data inspector in this case before delivering this to the vertical mapper user, in this case to examine and see that how this would look in 3D in this case. So how are you doing it on time? In this case. Now, we also experimented here with doing some raising of water levels here. We used the raster expression evaluator. I took the training shop in rasters previously here, and I saw that you now have a raster cell value replacer, which kind of makes this operation much easier, because the expression evaluator's syntax to use is quite, well, kind of a pain. But it's very powerful if you understand it, which I quite don't yet, but I managed to get an example of FMPedia to get this to work, and using the raster cell queries, we could get some rough model of how, if we raise the water level half a meter, 1 meter, and 2 meters, how this would look. This is how it looks in the FME viewer now. So the result of this was included in the municipality's official planning and is available for everybody to look at. But it's also delivered with a report where the specialists have made a thorough analysis of other things affecting this too. And some major conclusion at this stage is what I think it's quite important to recognize people's expertise in different areas, especially when we have such a wonderful tool like Workbench, where it's easy to do stuff quite fast, but someone has to really analyze and understand what it means, and so to get a correct result. And also there is now, with the help of the FileName and PathName reader, there is excellent batch processing capabilities inside the Workbench. Now, good, or maybe I should, heavy spatial ETL, it's quite clear it demands a strategic approach. I know that Peter has a lot of experience in this, but it gets much clearer when you use these 3D data sets, and especially with lighter data and stuff like that. And there's also this thing, always visualize data to understand it. This is kind of a, when I started out working, I got a mentor, I can say, a colleague I've been working with for 15 years almost. He's kind of my Obi-Wan Kenobi in ETL. He says, like, so always visualize data before you deliver it. And it's quite true, because it's surprisingly often you get a data set that the one who delivered it obviously didn't look at it before he sent it over because there's something wrong with it. But if you're now working in 3 dimensions, we should be able to view it in 3 dimensions. And this gets increasingly important. So the data inspector in 3D is very warmly welcomed in this case. And to illustrate this, the importance of the 3rd dimension in this case, it's I made a little tool with the FME in this case. As I told you before, we have specialists that can relate to the different tolerances if you generate a digital elevation model. But I kind of wanted to figure out on my own, what does it mean if I use a 2-meter resolution elevation model, or 1 meter, or if I use 10 centimeters. So I made a little tool that automatically reads the laser data files, creates the digital elevation model. It's a little custom transformer here, and you can set different interpolations algorithms in these. So you can say you have a sample file, and you can actually get 3 cross sections of this with the different tolerances. And the result of this is a part of these tiles, and I throw in a line like this just on the diagonal, and then I can look at the result like this. This is so it's simple cross-section analysis just by using the Workbench and routing to the viewer. Now, if I had the spatial data inspector in this case, I would of course examine it in real 3D. But this is the profile, and the interesting thing is that this is the cross-section here. It's probably somewhere close to the rimmer, and this, if I use a 10 centimeter resolution, and this is how it looks in this case. And if I go to 1 meter in this case, which sounds pretty high resolution, but if you look at hydrological models, you can see that this really can make a difference. The resolution can make a difference. Even if I'm not an expert in hydrology, I can understand if there comes water pouring down here, it will definitely miss this kind of hole here if I use 1 meter or if I use 2 meters in this case. I kind of started a bit early of this, so any questions about this? Oh, thank you.